Continuing here with the factors that are affecting the oxygen binding to hemoglobin. So we finished up the previous section. We were talking about how the pH, the temperature, and the CO2 concentration, those are the factors that are really affecting the oxygen binding to hemoglobin. So here's some more information. The Bohr effect is a shift in the hemoglobin saturation curve that results from a pH change. So that's our first factor right here. And then also if you are in chronic hypoxia, so hypo means below, you don't have enough oxygen for an extended period of time, then you will increase the production of a chemical known as 2,3-DPG. And I wrote it out here for you guys. It's 2,3-diphosphoglyceric acid. And this chemical, 2,3-DPG, decreases the affinity of oxygen to hemoglobin. That means it makes it easier to release oxygen into the blood, or into the tissues, and that makes sense because if you're chronically oxygen deprived, or chronic hypoxia, you want to make sure that you still deliver a good amount of oxygen to the tissues, so you want to decrease the affinity of oxygen to hemoglobin. And here is your summary slide of arterial oxygen. You can take a look at these flow charts right here. So oxygen dissolved in plasma, we said it was a ridiculously small amount. And it has all sorts of factors here that are affecting it. But keep in mind that oxygen dissolved in plasma is only 3 milliliters out of 200 total that are bound to hemoglobin per liter. So here the vast majority, over 98% of the oxygen that travels in the blood is bound to hemoglobin. And of course the factors that are affecting the saturation of hemoglobin are the concentration of CO2 or partial pressure of CO2, the pH, the temperature, and the amount of 2,3-DPG. And then also the total number of binding sites that are available, and that's the hemoglobin content per red blood cell and the number of red blood cells overall. So overall, of course, if you're taking a look at arterial oxygen content, so we're going to include this here is your important part. Over here, this is a very small amount. It's only like 1%, 1.5% of your total oxygen that is carried in the blood. The vast majority is always going to be bound to hemoglobin, and these factors matter so much more than what's going on over here. So oxygen dissolved in plasma, again, as I said, this is such a small amount that I don't even want you to bother much with this. And there are some factors that are affecting that too, but we shouldn't be paying too much attention to this. What's important is the total arterial oxygen content. And so that's the same chart as before, just a little bit bigger. The percent saturation of hemoglobin is affected by the partial pressure of CO2, the CO2 concentration, that is the pH, temperature, and the amount of 2,3-DPG that's around. And the total number of binding sites, of course, depends on how much hemoglobin you have per red blood cell and the number of red blood cells you have overall. So that concludes our discussion of how oxygen is carried in blood. Now we need to move on to carbon dioxide. And believe it or not, this is actually more interesting than oxygen, because oxygen, the vast majority, is carried on hemoglobin. We have this wonderful molecule, hemoglobin, and it's perfect. And in the amount of oxygen that it can carry and release to the tissues, and it's very well balanced in the way it receives and then gives off the oxygen. Now let's take a look at carbon dioxide. Do we have another molecule such as hemoglobin that now takes care of the carbon dioxide transport? And the answer is no. So now what do? We have significant amounts of CO2 that are waste product of aerobic respiration. So how do we get it back to the lungs and get rid of it? Well, here's the deal. 7% of your carbon dioxide waste load will be dissolved in plasma. And so we saw earlier that even oxygen can dissolve to some extent in plasma. It's not much, but it's some. And CO2 is not different. It also can dissolve to some extent in plasma, but that will be only 7%. Now what happens to the rest? We still have to deal with 93%. Well, the vast majority of the CO2 will be converted to bicarbonate ions, and that is 70%. And the remaining 23% will be bound to hemoglobin, where it's basically hiding in the hemoglobin. So the hemoglobin also binds the hydrogen ions that are the product of this reaction that we'll take a look at in a minute, and that you've seen before, by the way. And some of the CO2 simply just hides in the hemoglobin protein, and then we call that carbaminohemoglobin. Now, we really need to take care of these 70%, and that means if it's converted to bicarbonate ion, well, you should be familiar with this equation. It's still the equation CO2 plus H2O forms carbonic acid, H2CO3, and that dissociates into hydrogen ions. Those are these guys right here that can also hide in hemoglobin, plus HCO3 minus bicarbonate ions. These are the bicarbonate ions right here, these guys. So right here. So, and let's take a look at this. Here is your all-inclusive chart, and I like this very much. So this is the carbon dioxide transport summary. So as we said, 7% will be dissolved in CO2. That's kind of easy, makes it nice and easy. Here's your cellular waste product, CO2, and it goes down, its concentration gradient dissolves in plasma. 7% will be dissolved in plasma, just a gas dissolved in a liquid. Now, 23%, let's do the other part that's easy. 23% will sort of hide in the hemoglobin molecule, sort of this gas CO2 sort of loosely attaches itself to hemoglobin, sort of non-specifically. That will be here, CO2 plus hemoglobin sort of forms this carbaminohemoglobin, 23%. The rest, the remaining 70%, so the vast majority, will undergo this equation. CO2 plus water forms carbonic acid. There's an enzyme in red blood cells that helps that process. This is called carbonic anhydrase. The Ca right here does not stand for California. It stands for carbonic anhydrase. And it helps the conversion of CO2 plus water to form carbonic acid, which then dissociates into bicarbonate ion and hydrogen ions. The hydrogen ions, they hide also in the hemoglobin and sort of form this hydrogen associated hemoglobin. Now, this stuff starts to accumulate. This bicarbonate right here starts to accumulate, and once concentration gradients are very different inside and outside of cells, stuff tends to go down its concentration gradient, and bicarbonate is no different. Bicarbonate starts to leave the cell because the concentration gradient is so steep that it will leave the cell, it will move out of the cell. Now we're losing a negatively charged ion here, so we have a HCO3 minus, so it carries a charge. And as the bicarbonate ions are leaving, this leaves us with an electrochemical imbalance. And in order to balance that out, we're inviting another negatively charged particle back inside of the cell to balance us out. And since chloride ions are in higher concentration on the outside, that makes the perfect candidate. So we're going to invite chloride ions to come into the cell in exchange for bicarbonate ions leaving. That is called the chloride shift. Once we are going to the lungs, we're going to do the opposite. We're going to do the reverse chloride shift. In this case, we are saying, well, we're getting rid of so much CO2 here right now, so we're keep the CO2 is diffusing from the plasma and from the hemoglobin into the alveoli, and we're breathing it out. So now we all of a sudden have a shortage of CO2. So now we're going to say, okay, well, we still have all this bicarbonate. And so what we're going to do is we're going to invite the bicarbonate that we just kicked out. We're going to invite it back in, and we're going to kick our chloride back out. So reverse chloride shift. And we're going to convert the bicarbonate to carbonic acid, which then dissociates into water and CO2, and there we have more CO2. So basically, as you're getting rid of CO2 by breathing it out, you need to invite the bicarbonate back in this reverse chloride shift, exchange for chloride out in this case, and then that sort of replenishes our source of CO2. We're going to do this in steps because I realize this is not the simplest thing that you've seen. In cellular respiration, you have a waste product. It's called CO2. 7% of that CO2 that's leaving the cells and moves into the blood by diffusion, 7% just dissolves in plasma. 23% will bind to hemoglobin and form carbaminohemoglobin. The vast majority will combine with water to form carbonic acid, H2CO3. This H2CO3, the carbonic acid, will dissociate into bicarbonate ions and hydrogen ions. The hydrogen ions will bind to hemoglobin, forming this hydrogenated hemoglobin. As the concentration of bicarbonate increases, there is a concentration gradient that will basically allow the bicarbonate to leave the cell. And in exchange for another negatively charged particle, we're inviting the chloride ions in that are in high concentration on the outside. That is known as the chloride shift. Chloride shift. Okay. Sorry, this is supposed to be a C, by the way, C, chloride shift. Okay. Now we're moving to the lungs, and in the lungs, we're breathing out CO2. So now the CO2 that was dissolved in the plasma, it diffuses into the alveoli of the lungs. We're breathing it out. Also, the carbaminohemoglobin, we're getting rid of the CO2, and by diffusion, it moves into the alveoli, and we're breathing it out. As we are losing more and more CO2 into the alveoli of the lungs right there and breathing it out, we're going to have to decide, hey, we need more CO2. So we're inviting the bicarbonate that we just kicked out. We're inviting it back in, and we're kicking the chloride that came in exchange, we're kicking it back out. That's known as the reverse chloride shift. Reverse chloride shift right here. And then we're following the equation that we're inviting the hydrogen ions back onto the bicarbonate, making carbonic acid, which dissociates into water and CO2, and we're breathing out the CO2. And that's the next slide right here. So we are inviting we're kicking out the chloride, we're inviting the bicarbonate back in, and then we need these hydrogen ions. And now we can combine these hydrogen ions with the bicarbonate ions, the hydrogen ions plus bicarbonate ions. We're making carbonic acid, which then dissociates into water and CO2. So we have more CO2. We're basically replenishing our resources of CO2. And the majority here diffuses down the concentration gradient into the alveoli of the lungs, and we are exhaling it. And here is another image showing you the very same thing. Carbon dioxide transport in a chloride shift. So again, in the tissue cells, we have plenty of CO2. And here the numbers are slightly different because this is from a different book, but never mind the difference in the numbers, the exact numbers, it doesn't really matter. 7% previously, now we have 10% dissolved in plasma, 20% here as carbaminohemoglobin hiding in hemoglobin, and the rest undergoes the chloride shift. And here you have it labeled, and that's why I kind of like this slide here. The chloride shift means that the CO2 that combined with water to form carbonic acid and then dissociate it into hydrogen ions and bicarbonate ions. Now, the concentrations of the bicarbonate get so high that it leaves the cell by diffusion, and we're inviting the chloride in. That's known as the chloride shift. And the reverse chloride shift in the lungs, as we saw previously. Now we're exhaling a lot of CO2 where it's diffusing into the alveoli of the lungs, and now we need to invite the bicarbonate that we just kicked out. We need to invite it back in. We're kicking the chloride now back out, and so therefore known as reverse chloride shift. And so now we're forming our carbonic acid again, which dissociates into water and CO2, and we're getting rid of the CO2 by exhaling it.